Hello everyone. In the last session, we talked about the concavity, the open intervals where the function was concave up and concave down. In this video, we're going to be talking about the second derivative test. Now, we can also use the second derivative to perform a simple test for finding relative maxima and minima. Now, this test is based on the fact that if the graph of a function is concave upward in an open interval containing c, and the derivative at that point, the derivative is 0. See this one? That is kind of your critical numbers. Then f of c must be a relative minimum of f. Similarly, if the graph of the function is concave downwards on an open interval containing c, and f prime of c is equal to 0 there, then f of c must be a relative maxima. Okay, let's look at the graphs here. Now, notice this is a function. The second derivative is positive. That means the point c over here is actually, if we draw a horizontal tangent line, that is f prime of c is 0 there, that point is the point of relative minima. On the other hand, if you have a concave downward graph and at the point C where you are able to get a horizontal tangent line and f prime of c is 0, this point C is a point of relative maxima. Okay? And at that point also the second derivative is strictly less than 0. Okay, so let's formally introduce the second derivative test. Let f be a function such that the first derivative is 0 at a point c, and the second derivative of the function exists on an open interval which contains c. Now, if the second derivative at c, when evaluated at c, is strictly positive, that is strictly greater than 0, we say that the function has a relative minimum at c and f of c. If the second derivative evaluated at c is strictly less than 0, then f has a relative maximum at c and f of c. You know, like your graphs here, think of this as a graph. So this is point of relative maxima. You have a concave downward, and this is the point of relative minima, which is, you can see, concave upwards. Okay, but when the second derivative, if f double prime of c, is 0, then the second derivative test fails. F may have a relative maxima or a minima or neither of them. In the scenario where the second derivative is 0, we cannot apply the second derivative test. We have to go to the first derivative test. Okay, let's go ahead and look at some examples. The first example, find the relative extreme of this function minus 3x5 plus 5x cubed using the second derivative test. Now remember, the second derivative test, the function has to be differentiable, second differentiable, and we would be looking at the points which is where this first derivative is 0. So what you do is, the first step is we find the x values where the f prime of x is 0. So when you put that, you get this function to be negative 15x4 plus 15x squared, which you can write as 15x squared 1 minus x squared. So it's kind of finding the critical numbers where the function has a horizontal tangent line. And the points where it has that, it is x is 0 or plus minus 1. So you look at this graph where minus 1, you have a horizontal tangent line, a horizontal tangent line in 1, and a horizontal tangent line at 0. Okay, now you want to find out whether the function has a relative maxima or minima at either of these 3 points. Okay, what do? We take the second derivative and we get it to be negative 60x cubed plus 30x or 30x 1 minus 2x squared. So from the graph we can see 0, 0 is not a point of relative minima or maxima, but minus 1 and 1 are. So let's verify using the second derivative test. So we applied the second derivative test on the critical number 0 plus minus 1. What are the points? Minus 1 and minus 2. Remember, this is C and f of C. So which is minus 1. And remember the function f of x is minus 3x5 plus 5x4. So when you put minus 1 here, then the answer is minus 2. Similarly, 0, 0, and 1 and 2. Then you're going to look at the sign of the second derivative. So evaluate the second derivative at minus 1, positive. 0, test is definitely failing. And the second derivative at 1 is a negative value. So that means at 1, it has a relative maxima. And at minus 1, it has a relative minima. And it is also very clear from the graph here. Minus 1 relative minima, 1 relative maxima. And 0, 0, there's nothing. And also, which is quite clear from the second derivative test. So we would like to know, still apply the first derivative test at x equal to 0 to see, to make it clear that it is not a maxima minima as we saw it in the graph. So let's go ahead and apply the first derivative test. So apply the first derivative test by looking at the following. So first of all, remember, we just have to look at the 0, not anywhere else, okay? So remember the graph of this function. So you have a graph here which goes like this, down, and then like this, and then something like that. So we are trying to see what happens near 0. So that's the only interval we need, minus infinity to 0, 0 to infinity. I'm picking up a point very close to 0 from the left-hand side. So the test value is minus 0.5. So in other words, here's 0. Remember, this is a critical number, so we use this little, hints to help us out, the visual clues. We're going to put our little test values, minus 0.5 and 0.5. So what is the first derivative at negative 0.5? It's a positive value. And the first derivative at 0.5 is also a positive value. So it's increasing and increasing. Also from the graph, you could see it's increasing and increasing. So clearly, the function has neither a relative maxima nor a minima at the point 0 and 0. Okay. Now, let's look at another example. We would like to find the relative extrema. In other words, what are the values of the function where you can see the maximum or minimum value and their relative maximum minimums. But we're going to apply the second derivative test to do it. So the usual, we would find the x values where the first derivative is 0. That means we're looking at the critical numbers which are given by the horizontal tangent line of where the function has a horizontal tangent line. So f prime of x is 0. We get minus 4x cubed plus 12x squared plus 16x, which I can combine. It's a cubic function. I can, factor it into minus 4x, x minus 4, and x plus 1. So, okay. So when f prime of x is 0, we get x to be minus 1, 0, and 4. Okay, so these are our critical numbers where the function has a horizontal tangent line. Okay, now then we find the second derivative. The second derivative is negative 12x squared plus 24x plus 16. And you can take the negative 4 common. You could get 3x squared minus 6x minus 4. Now remember, we have to apply the second derivative test to find the relative maxima and minima. We will be testing it on the points minus 1, 0, and 4. So the points are minus 1 and 3, 0 and 0, 4 and 128. Keep in mind, these values are given by, so this is x and this one is f of x. So if my x is minus 1, this is f of minus 1. And remember your function f of x is negative x4 plus 4x cubed plus 8x squared. Okay, so then we look at the sign of the second derivative at each of these points. At minus 1, it's negative 20. So that means it's less than 0. That means the function has a relative maximum at minus 1. When at 0, it is 16, which is positive. That means the function has a relative minimum at x equals 0. And at second derivative at 4 is a negative 80. That means it has a relative maximum. So the second derivative test gives us this, and you can easily see it here. So this is one little point here, this is point 0, the point negative 1, and the point 4. So you see all these little 4 points where you see the second derivative test. Okay, so now we'll continue to the next example. Okay, this is this is the second derivative test. Okay, find the relative extrema of this function, sine plus cosine, from 0 to 2 pi. And clearly from the graph, we can see that the function has a relative extrema at some point over here and at some point over here, which is around, say, pi halves and 3 pi halves over here. Okay, so clearly this is a continuous function. It's going to be, these are sines and cosines. They are differentiable many times, so they're also differentiable second times too, 2 times 2. So the first thing we do is to find where the relative extrema is. We find the x values with the function derivative is 0. So the derivative of this function is cosine x minus sine x, and when you put this to be 0, it means what are the values where cosine x is sine x. Now if you remember from the all students take calculus, so the function where cosine and sine have the same value is at pi fourths and at 5 pi fourths. These are the two places where the function cosine and sine have the same value. So we have got our critical numbers here. Okay. So now we're going to look at the second derivative. So find the second derivative is minus sine minus cosine. Okay, so yes, that's the second derivative. Okay, so when we apply the second derivative test on pi fourths and 5 pi fourths, so you look at the points pi fourths square root 2 and 5 pi fourths negative square root 2. The second derivative at pi fourths is negative. That means it has a relative maxima at pi fourths and square root 2. A little off it seems. Remember I said pi halves, no, it's pi fourths, and it has a relative minimum at 5 pi fourths because it is a positive value when you substitute in the second derivative. Okay, so we have done some examples for applying the second derivative to find the relative maximum and minimum. And so the next step is to do some practice problems. So go ahead, guys. Practice on these 4 problems. Apply the second derivative test to find the relative extrema of the function. Thank you.